You can, I think you're close. Okay. If you guys have any questions, I like questions, please just stop me, unmute yourself and just ask the question. Just interrupt me. I like being interrupted and I think it's valuable for the rest of the students. So just feel free to just unmute and ask your question out loud. Okay. So as I said, my goal here is to convince you of the magic of cryptography. There's a lot of magical concepts in cryptography. It was hard to choose, but I chose two of them, one for today's lecture and the other one for Thursday's lecture. So the first one, I'm going to show you, like a real magician, how to generate randomness out of thin air. Okay, so that's what we're going to see today. And next lecture, I'm going to show you how to convince you that something is true without teaching you anything, you learning anything about why it's true. That's what's called zero knowledge proof. Again, like a real magician, you know how this was kind of Cody's really cute way of thinking of it. You know how magician shows you magic, but you learn nothing about how to do it. We're going to see how to do that in using cryptography. So, okay, but today we're going to talk about how we generate randomness out of thin air. And let me start with kind of the bread and butter of cryptography, which is encryption. So what is encryption? So I have Alice wants to send a message, let's say M to Bob, but secretly. So usually the way it works, they both share some secret key K that both Alice and Bob know. Then when Alice wants to send him a message, she encrypts it. So encryption is a function of their secret key and a message M to generate a ciphertext C. And what we want is confidentiality, meaning an eavesdropper here in the middle that sees the communication, he sees the ciphertext, he has no idea what the message is. So he's eavesdropping, but he cannot tell what the message is without knowing the key. Of course, Bob knows the key, so he can decrypt. So just the mechanics of an encryption. So what is encryption? It consists of three parts. First, Alice and Bob generate a shared secret key, K, known only to them. Then, oh, what happened? Okay. Then Alice, when she wants to send a message to M, she uses the key to encrypt the message M. So she generates a ciphertext C, which is an encryption of K, the key K, and M. And then Bob, who gets the ciphertext, can use the key K to decrypt. So there's the decryption function denoted by D for decrypt that takes the key, the shared key, and a ciphertext and recovers the message. Okay, so the correctness property is that when you decrypt using the shared key, an encryption that a ciphertext that encrypted M, then you should get back the original message M. So what an encryption scheme is. And for security, we want to say that if you do not, an eavesdropper who does not know K and sees only C cannot decipher C. So this is what an encryption scheme is. By the way, can you see my mouse when I'm hovering? Yeah, okay, good. So here's the first kind of formal encryption scheme that I know of. It's the one-time pad by Vernon in the beginning of the 20th century. And here's how he proposed to encrypt messages. So first, what is the shared key? It's just a random bit string. Okay, so just a string of 0 1s, that's the key. Now, when you want to encrypt, what do? You take the key, the shared key, you take the message, where you think of the message as also being just a bit string. And what you do, you just XOR bit by bit. So the ciphertext C is just, you take 0 XOR 1, you get 1, 1 XOR 0, you get 1, 1 XOR 1, 0, and so on and so forth. Okay, that's how we propose to encrypt. Just you take the key and you use it to mask the message by XORing it with a message. Any idea how to decrypt? So now I have a key, I get a ciphertext. How do I decrypt it?
XOR it again.
Exactly, precisely. You XOR it again. So what you do, you take the key, you XOR it with the ciphertext. Now what you get, the key XOR with the ciphertext, which is K XOR M, which is nothing but kind of key XOR with the key, which is 0, and XOR with M, which is M. So you get the correctness property. So this is a very simple example of an encryption scheme. And now let me ask you, is it secure? Is the encryption scheme secure? Now, in order to answer that question, you need to, so, okay, I guess first I feel like, yes, it should be secure, because at least if you use the key only once, because no matter what the message is, you know, an eavesdropper who does not know K, since K is random, an eavesdropper that sees K, X, or M, K really masks the message, right? So it completely randomizes kind of the message, and it seems like it's secure. But this is a very intuitive explanation. And actually, to understand if it's secure or not, one needs to first ask, what is security? What does it mean for encryption scheme to be secure? And this is a bit of a detour. We'll get to the generating randomness in a bit, but I want one of the also kind of really interesting things in cryptography is actually defining what are the right notions. And I want to do a quick detour and kind of go through this process of how would you define a secure encryption? Okay, so again, we're asking if this, we have a scheme here, a very simple, elegant scheme. We're asking if it's secure. And to answer that question, we need to understand what is security. So how would we define it? How about this? Let me first attempt. An eavesdropper, Eve, cannot learn anything about the message M. Does the one-time pad satisfy this definition? Again, Eves does not learn anything about the message M. So even though maybe I convinced you that the one-time pad is secure and so on, I want to argue that it doesn't satisfy even this definition, even just once. Why? Eve learns the length of the message, for example, right? So she does learn K, X, or M, which reveals the length. So she does learn the length, okay? So you can't say she doesn't learn anything. Maybe she doesn't learn anything except for the length. Okay, so here's another attempt. Eve does not learn anything about the message except its length. So do we achieve this? And now, again, it's like, what do you mean she doesn't learn anything about them? What does that even mean? So one can say, I mean, we need to be precise here. So one can say, okay, how about this? Eve cannot predict any bit of the message with probability better than half. Okay, do we achieve this? Again, the security means Eve cannot predict any bit of the message with probability greater than half. Of course, probability half she can guess, but we want to say secure, she cannot do better than guessing. Does the one-time pad achieve that? Even just once? And if I want to say the answer is no, because maybe Eve knows something about the message. Maybe she knows that the message always starts with the first, let's say, least significant bit being 0. Or, if she knows it's encoded, the message is encoded in a certain way, then maybe she has some information about what the bits are. Maybe she knows that usually I start with hello. So she knows the first, bits of the message. So she can predict. Maybe she can never predict. Maybe she has a priori information about the message. So this is just to show you that even just defining security is very subtle. Okay, so here is another attempt, okay, that Eve learns nothing about N, about the message, by seeing the ciphertext. Okay, so she may know more, but by seeing, she doesn't learn anything. She may know something originally, but by seeing C, she doesn't learn more. So how do I want to formalize it? Here's the formality. For every two messages, M and M prime, of the same length, because remember we said the length is revealed, every two messages, M and M prime. If you see a ciphertext that encrypts M and a ciphertext that encrypts M prime, these are distributed identically. Every distribution. So she may know ahead of time a little bit what, some information about what was encrypted, what the message encrypted, but the ciphertext doesn't give her any more information. Because the ciphertext, it has a distribution no matter what message you encrypt. Okay, now that's the definition, and moreover, the one-time pad actually satisfies this definition. It is secure. And we'll see that that's going to be part of the homework assignment. That's going to be our first homework assignment, is to prove that the one-time pad is secure under this definition. Okay, good. So, okay, so what am I talking about? Generating randomness or blah, 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 encryption. We have the most simple solution right in front of us. And I'm telling you, it's secure. So, maybe we should all go home. But this is a good definition in the sense that it satisfies, the one-time pad satisfies, and it is meaningful, but it's really weak. And the reason why it's really weak is because it says if you see only one encryption, one ciphertext, it's identically distributed. But what if you see many kind of ciphertext, not just one? And with the one-time pad, and that's why it's called one time, if you see two ciphertexts, it's no longer secure. So the two-time pad is not secure. And let me explain what I mean. So suppose the same key is used to encrypt two different messages. So let's say we have ciphertext 1, C1, encrypts message M1, and ciphertext 2 encrypts M2. Now I want to say, if the adversary, if the eavesdropper sees both C1 and C2, she can learn something about M1 and M2. For example, here's what she can. She can store the two ciphertexts, and that gives her information. What information does it give her? So let's see, when we XOR these two ciphertexts, what do we get? Ciphertext 1 is just the key XOR with message 1. We XOR it with ciphertext 2, which is the key XOR message 2. By reordering the terms, we get the key XOR with itself, which is 0, XORed with the XOR of the two messages. So now it can learn the XOR of the two messages. That does reveal information. And that's a problem. So from this, you can figure out some information. And actually, this was an attack used in World War II. It's called Project Venona, where the United States learned information from about ciphers used by the Soviet Union, and it's exactly these types of attacks. So the one-time pad is only one-time secure. You can use the key to encrypt a single message. But of course, we don't want to only encrypt one message. We want to encrypt many messages using one key. So what we really want is a many-time secure encryption. What does a many-time secure encryption mean? It means that for every L being number of messages, and for every kind of sequence of messages, M1 up to ML, and M1 prime up to ML prime, if you see the encryptions, the ciphertext of M1 up to ML, it has the same distribution as the encryption of M1 prime up to ML prime. So in other words, I can encrypt many messages under the key K, and the distribution of my ciphertexts will look the same, whether they're encrypted M1 up to ML or M1 prime up to ML prime. So this is kind of a many-time secure encryption. And really, in reality, this is what we want, a many-time secure encryption. We want to be able to use our key to encrypt more than just one message. Okay. Actually, before we go here, are there any questions so far about the one-time, the many-time, the security definitions, the one-time pad? Is it clear why I want many-time encryption to encrypt many messages, not just one? Okay, so now hopefully you're convinced that that's really what we want. But unfortunately, such a thing does not exist. That's pretty sad news for us because we really need a many-time secure encryption. We don't want to, just encrypt once. And I'm not going to prove why a many-time secure encryption doesn't exist, but let me give you an intuition why it doesn't exist. And what I'm saying here is not just the one-time pad is not many-time secure. You can't come up, there does not exist any encryption scheme that is many-time secure. And let me tell you intuitively why such a thing does not exist. So intuitively, when you see a ciphertext, you don't even know the message M1, which is encrypted. Sometimes we maybe you know that in the morning I send an encrypted message saying good morning. Now, if you know the message M1, this ciphertext does leak something about the key. Because if I encrypted it with one key or with another key, will look different. So in fact, every ciphertext, kind of, especially if you know information about the message encrypted, it leaks some information about the key. And now you essentially, when there's too many ciphertexts, too much information is leaked, and then security gets lost. That's the intuition for why many times secure encryption doesn't exist. So where are we? Where are we now? So we have the one-time pad, which is very nice, but the length of the key needs to grow with the amount of bits I want to encrypt. So that's really bad. You know, we need to meet once to share a key, but how big of a key we need to share? We need to have like a suitcase, a huge suitcase full of bits, because, you know, we can use each key only one, each bit only to encrypt one bit message. That we can do with the one-time pad, and this we can't do any better. So this is kind of a sad state of affair. And now let me tell you one really beautiful thing, and I think what makes cryptography just amazing, is that I think I view cryptography as the art of overcoming negative results. So there is no impossibility in cryptography. An impossibility is just an invitation to overcome the impossibility. Okay? You just change the rules. You know, a lot of things about cryptography seem impossible. And that's why cryptography is so magical. Okay. So now that's where kind of generating randomness comes in. I'm going to show you how to get many times secure encryption. I'm going to overcome this negative result. And the way I'm going to do it is by generating randomness out of thin air. And I'm going to show you how to generate randomness out of thin air. That's what I'm going to do next. But before I do that, you may think, okay, what does generating randomness have to do with everything I said so far? It seems disconnected. So let me just, we're going to connect it later, but just to give you a hint, the reason it's connected is because if we can share a short key, but then kind of use the short key to generate more and more and more and more secret randomness, then we can encrypt more and more and more bits, and we can have many-time encryption. So that's why if we can take short randomness and generate more and more and more and more randomness out of it, then we can do many-time encryption. We can use a short key, we can generate as many as one randomness, and we can kind of encrypt more and more and more. That's how we get many-time. But now, you know, so that's what I'm going to tell you next, how to generate randomness out of thin air. Now, at this point, you can say, come on, what do you mean generate? You can't generate randomness out of thin air. And so, but I'm gonna, again, change the model and show you how to do it. Okay. But first, let me again do the connection to cryptography to encryption a little more modular. And so, okay, so suppose I have a function f, a deterministic function f that generates randomness. Now, what do I mean generate randomness? Suppose I had a function f such that for a random key k, for any n, my n can be much, so for random key k of size L bit key, for any n can be much larger than L. Suppose I had this deterministic function that miraculously, such a thing can't exist, but suppose I had this function such that satisfies that the function on key and 1, think of it as a bit, think of this function as outputting 1 bit, and the function on key and 2, and the function on key and 3, and so on and so forth, up to the function key on n, outputs just a random bit u1, random bit u2, up to a random bit un. So suppose I have this function that you feed him one key, it's one random key, these keys are all the same, one random key, which is short, it's of size L, and it manages to output n random bits. Now, we all know that this is impossible. You can't take a deterministic function with, you know, entropy and feed it kind of min entropy L or entropy L and get entropy N, more entropy deterministically. You can't deterministically generate entropy. We know that. But if let's dream big, we can do that. Okay? We can use SKI to encrypt the ith message. Let's think of the messages as being bit. Okay, just break your messages to bit. Now you can encrypt as many bits as you want. For the ith bit, you use SKI, which is completely random, to encrypt the ith bit. Because for every n, for any number of bits you want to encrypt, much bigger than L, for any n, you know, this is a good, all these U's are good one-time pairs because they're all random together. They're just random. Look, they're just uniformly distributed in 0, 1 to the n. So now you can use this to encrypt the ith message, and that's how you get many times secure encryption. Any question about this? So if I had this magic of taking a short key and using it to generate as many random bits as I want, then we have many times secure encryption. For that, what we do to encrypt the ith bit, we just use SKI as the key for the one-time pad. So we just take this function and XOR it with the ith bit we want to encrypt. Okay, questions so far?
I had a question about like this procedure. At some point, when you need to feed back the random bits back into the algorithm to avoid revealing too much information about that initial K.
Mm-hmm. Oh, you're asking if it reveals information about the initial K?
Yeah, eventually,
okay,
would it?
Okay, so look, of course it seems like it should, but if I had the guarantee that, look, these are all random, then it essentially says, no, it doesn't reveal information about the initial K, or it doesn't reveal the initial K, because if these reveal the initial K, then we can say that fkn plus 1 is random. So I agree with you. It seems like it does. That because the point is this thing doesn't exist. It's a pose. It's like, okay, good. So Grant, you have a very good question. And essentially what you're saying, look, you're in dreamland. It's impossible because exactly like you're saying, look, I convinced you before that these things do give information about K. So eventually you give information about K. So once you give information about K, fkn plus 1 will not look random. So it's like if it, but it's dream world. This can't exist. So you have the right intuition, but what I'm going to show you for the rest of this lecture is how to do it using my magic. Okay, so we're now moving to the magic. Any question? This was all kind of setting up, set up for the magic. Any questions? Please ask questions. If there's something that's not clear to you, I'm sure it's unclear to many others, so it's good to ask. Okay, so here is the magic. It's true. We cannot generate true randomness. And Grant, your intuition was completely right. That's impossible. But what we can do, and it's enough for us, is to generate computational randomness. Now, what do I mean by computational randomness? What I mean is, I cannot say that FK1, FK2, FKN, and so on and so forth are random. They're not random. But what I can say is that they look random. Maybe they're not. They look random. So, by the way, before I continue, I don't know if anyone was confused by this, but let me just make sure. You didn't ask, but just make sure. These K are bits, and now I'm putting 1, 2. They're not bits anymore. So, of course, you can encode this 1, 2 up to n using binary bit strings. So you can still think of F as being like 0, 1 star to 0, 1. I don't know if you guys were confused by kind of having half bits and half numbers. Okay. But that's a side remark. Okay, so what I'm going to show you again, I don't have an F that really generates entropy. Okay, I can't generate entropy or randomness out of thin air. But I'm going to show you how to construct a function f such that k1, fk2, and so on and so forth, as much as you want. It's not random. I can't say that this is distributed like n random bits, but it looks like it is. Now, what do I mean it looks like it is? I mean that these distributions on the left and on the right are not identical, but they are what we call computational indistinguishable. So what do I mean by computational indistinguishable? What I mean is that an adversary that runs in bounded amount of time, let's say polynomial time, that's for us efficient. Okay, so an efficient adversary, we in theoretical computer science, we model efficient adversaries as adversaries or efficient algorithms as algorithms that run in polynomial time. So any polynomial time algorithm cannot distinguish between the distribution on the left and the distribution on the right. Now, let me mention, these distributions may be very, very different. Very different. They may have very large statistical distance. But a computationally bounded algorithm, a polynomial time algorithm, cannot distinguish. So that's what I'm going to do. I'm going to construct for you a function f that doesn't really generate randomness out of thin air, but it looks like it does. For the crowd, you know, I'm the magician. For the crowd, which are adversarial, which are polynomially bounded, then I generated randomness. That's what a real magician. You know, they don't, you know, cut a woman to half and put her back apart. But for us, it looks like they did, right? I'm going to do the same thing. Okay, I'm going to construct a function. It won't really generate randomness. But for the polynomially bounded algorithms or adversaries, it will look like it's random. And therefore, these polynomial time algorithms won't be able to break the encryption. Okay, so I'm going to construct an encryption that's not secure against an unbounded adversary, but only secure against polynomial time attackers, a polynomial time Eve. And that's today, all our encryptions are of that form. We don't get unconditional security like the one-time pad, like the one-time pad gives you. We get only computational security, and that's how we get many time, by relaxing the model from unconditional security to computational security. Okay, questions before I actually show you how to construct this function f? Okay, so here's the main insight of how to do this. And this is really, I think, I remember when I studied this as a student, my mind was blown away. So how do you generate something that looks random? The idea of doing that is to use hardness. Oh, so I'm going to show you how to use hardness to generate randomness, to generate computational randomness. That is my kind of magic. So as I said, I'm going to only be secure against computationally bounded adversaries. So I'm going to use something that's hard for them, that they won't be able to kind of compute. And for them, it will look random. That's kind of the idea. So let me be a little more precise. And for this, I need to give a few definitions. Any questions before we continue? Okay. So one of the basic assumptions in cryptography, probably the most basic assumption in cryptography, is what is called a one-way function. So what is a one-way function? A one-way function is a function f, let's say from 0, 1 star, star meaning any size bit string, to 0, 1 star. So from any length bit string to any length bit string, that has the following property. It's easy to compute. So given an input x in the domain, in polynomial time, you can generate f of x. You can compute the function efficiently in polynomial time. Yet, inverting the function given an element y, finding any preimage x such that f of x equals y, that's hard. Okay, that a polynomial time algorithm cannot do. This is what's called a one-way function. For that. Let me give you an example. There are many examples of one-way functions. One of the kind of most well-known ones is the following. It's a one-way function that takes as input large primes and outputs their product. So no, multiplication is easy. If I have two large primes, I can multiply them and I can easily compute. So if I have a large prime P, let's say n-bit string, which encodes a prime number P, and an n-bit string that encodes a prime number Q, given P and Q, I can efficiently compute n, which is P times Q. Okay, their product. How about inverting? If I have a random n, which is the product of two large primes, can I find the primes efficiently? So the truth is we don't know, but we really believe it's hard. We believe that factoring is hard. Okay, so assuming you believe that factoring is hard, you have a one-way function. Now, I lied here a little bit because I assumed that the domain has only kind of two large primes, whereas the domain is any number, so why would they be prime? So it's a bit of a cheat. To make this really a one-way function, you need to work a little harder, but that's kind of, you can kind of, that's what's called a weak one-way function, to actually make it one-way function, to say, okay, given f of x for a random x, it's hard. You can invert only with negligible probability, with very, very small probability. You need to do some more work. But this is an example where, you know, I have a function that if I choose a random x, which is two large primes here, then, and I give you f of x, the n, which is p times q, then inverting and finding p and q is hard. Okay, so that's kind of a basis for a one-way function. Okay, so this is a one-way function. At this point, it's not clear at all why it's how I use one-way functions to generate randomness, but we'll see that in a minute. Actually, we're not going to use one-way function. I mean, we can use one-way function to generate randomness, but what I'm going to show you today is something simpler. I'm going to show you how to use a one-way permutation to generate randomness. What is a one-way permutation? It's a one-way function, which is also a permutation. It's one-to-one and onto. Okay, so any two elements in the domain, they go, any two different elements in the domain go to two different elements in the range, and the domain and range are the same size. So if you think of f, let's say from 0, 1 to the n, to 0, 0, 1 to the n, and it's injective and on. Okay, that's a one-way permutation. Okay, so now what I want to do is I want to show you why, how to, if assume we have a one-way permutation, and now this is an assumption. I want to point out, I don't know if one-way functions exist. I don't know if there are functions that are easy to compute and hard to invert. But I believe there are. I under assumption. So if factoring is hard, then I have a one-way function. Another assumption, which you'll see in the homework, is based on discrete log. So here another function that is one way is, I have a question. How many of you, maybe just kind of raise your hand, how many of you know like what a finite group is? Like, did you take group theory in your classes? Okay, so few. Okay. Oh, you're raising more. Huh? Okay, it's good. Okay, so more. Okay, you're starting to raise your hand. Oh, okay. Okay, good. So many of you have actually. Okay, so another example of a one-way function, which you're going to see in the homework, is based on finite groups. So you don't need to know really what a finite group. I mean, even if you don't know what a finite group is, it's okay. A group has a single operation, as opposed to like addition and multiplication. It has only one operation. Think of it as multiplication. And here's another function that we believe is one way, at least in some groups. But let me actually give you an instantiation. Take elements mod p, where p is the prime. Okay, so you take elements, you take mod p. What f does is take a fixed kind of number, I don't know, maybe like number, let's call it g, but you can think of g as being 2 even. And what I do, I take an input x, the output is g to the x. Again, g is fixed. You can think of it as being any element between 1 and p, not 1, but like any element kind of in the middle. And so you take x and you output g to the x mod p. So computing, given x, computing g to the x mod p, we know how to do it efficiently. But given g to the x to the power of x mod p, finding x, we believe that it's hard. And that's called the discrete log assumption. And in the homework, you'll see the last problem is related to this. So the point is there are many one-way functions. All of them require some assumption. And of course they require some assumption. The reason is we don't even know if p equals np. So if p equals np, then one-way functions simply do not exist. And because we do not know whether p equals np or not, the existence of one-way function is an assumption. Okay, but we have instantiation. We have example of functions that we do believe they're one-way functions. Okay, so now suppose not only we have a one-way function, but we actually have a one-way permutation. Now I'm going to show you how to use this one-way permutation to generate randomness. And here's the basic idea. So suppose I have a one-way function f. F is a one-way function. If f is one way, it means that given f of x, it's hard to find the entire preimage x. Now if it's a permutation, so there's only one preimage, which is x. So now given f of x, we know that it's hard to find x. But maybe the first bit of x is easy to find. Maybe the third bit of x is easy to find. But we can't, all of this is hard. Suppose for a second there was one bit of x that we knew was hard to find. But what I mean by hard, it looked random. So suppose I had a predicate. Suppose it's like the p of x is like x, the ith bit of x. Suppose I had one predicate that was really, really hard. I could not guess. Given f of x, I cannot guess this predicate with probability better than half. This predicate looks random. Suppose I had such a thing. Okay, so again, this is kind of an important point. A one-way function, I want to repeat this because it's important. One-way function just says that given f of x, or a one-way permutation, given f of x, I cannot find x. It does not mean that I cannot find the first bit of x. It does not mean that I cannot find the second bit of x. It just means it's hard to find the entire x. But suppose there was one bit that was hard to find. Okay, suppose that there was like, let's say the first bit was really hard to find. Hard to find, I mean, even if you know f of x for a random x, this one looks random. The first bit of x looks random. Okay, so in other words, suppose I had a predicate of x. This is an efficient predicate, like the first bit, like an input x, output the first bit of x, for example. Suppose I had an efficient predicate that given f of x, this predicate looks random. Now, of course, it's not random. There cannot exist a predicate p that this is distributed like f of x in uniform. You can't, because especially if f is a permutation. If f is a permutation, x is determined here. And therefore P of X is not random at all. It's deterministic. P is deterministic. Think of P as the first bit of X. So of course it's not random. But suppose we had a predicate that looked random. Okay, so such a predicate that looks random is what's called a hardcore predicate. It's kind of where the core of hardness lies. Okay, so we say that P, a predicate P, an efficient predicate P, is a hardcore predicate if given the one-way function and given the one-way function and this predicate, this predicate looks random even given the one-way function, the image. So f of X and P of X looks like f of X in a random bit. Okay, that's the definition of a hardcore predicate. Now, here's the beauty. If we had a one-way permutation that had a hardcore predicate, then we just generated a bit of randomness. That's pretty amazing. Anybody see how you can, how using a hardcore predicate, you can generate a bit of randomness? Okay, we'll get to that in a second. We'll get to that. Use something to think about. So this is what, again, I just want to emphasize again, this is not the same distribution. It's only computational indistinguishable. Okay, so our hardcore predicate is a predicate P, so that f of X and P of X are not exactly distributed like f of X in uniform, but they're computationally indistinguishable from f of X in uniform. So a polynomial algorithm cannot distinguish between the case that this is the input or this is the input. Okay, it looks the same, or it can distinguish with only negligible probability. And I don't want to get into the definition, the formal definition of negligible and so on, because it will take too much time, and I want to keep kind of the big ideas here in today's lecture. But essentially, think you can think of it, he cannot distinguish, intuitively. Okay, before I show you how you use this to generate randomness, there's a beautiful theorem by Goldach and Levin that shows that every one-way function has a hardcore predicate. I'm not going to tell you exactly what the hardcore predicate is. It's actually a beautiful, beautiful theorem. I wish I had time to prove this. It's so, so beautiful. The proof is beautiful as well. But let's believe them and take this as a given. So every function f has every one-way function has some predicate, which is hardcore. Okay. Now I want to say, you take a one-way permutation, f, because it has a hardcore predicate, it can be used to generate randomness. And here is the idea. Here's how you generate randomness. This is it. This is the beauty. G is going to be a randomness generator. And here is how it generates randomness. It takes an n-bit random string, and it will generate an n+1 bit random string. Or not really random, but computationally looking random. How does he do that? G of X outputs f of X, which is, if X is random, f of X is random because it's a permutation. So it takes a random input to a random output. So this is random. But it adds to it one additional bit, and that's the hardcore predicate. So now it took my generator, my randomness generator, that's me being a magician. I'm going to generate randomness out of thin air. I'm going to take as input n bits of randomness. You're kind of my audience. You're polynomially bounded. And what I'm going to output for you, so you give me only n bits of randomness. I'm not going to tell you what X is, of course. Then G is efficient. So of course, if I tell you X, you can distinguish this from random. But you allow me only access to n bits of randomness. And I'm going to give you n+1 bits that you will be random. What are my n plus 1 bits? My first n bits is going to just be the output of the permutation and the n bits of randomness that I got. So this is f of x. It's n random bits. And I'm going to append to it some because this is the truth of f of x. So that's look for the audience of a polynomial algorithm like it is random. So for my audience, my polynomially bounded audience, you will get n plus 1 bits that look random. So I have access to n bits of randomness, but I generated from the perspective of a polynomial timed algorithm, which is all of my audience, I generated n plus 1 bits of randomness. That's it. I just generated for you randomness out of thin air. How did I do it? By using hardness. Of course, I can't really generate randomness, but I can use hardness, something that's so hard that in your mind, it's random. You can't distinguish it from random because you have no idea how to compute it. And in your mind, it's random. Okay, any questions? Okay, so good. So this is how we generated, oh, yes.
Quick question. So I think you were cutting off a little bit. So we didn't hear a lot of just the last bit about how you turn this extra bit to a whole random string. The punchline, we kind of missed that. If you could repeat it, that would be great. Thank
you. The best time not to, okay, sorry about that. Let me repeat it. I'm not really what you missed, but let me just repeat the last bit because it's really kind of the highlight of the lecture, in my opinion. Okay, so I'm the magician. I get n bits of randomness, and I'm going to generate to my audience, all of you who are polynomial time algorithms. You guys are polynomially bounded. I'm going to show you that I can generate n plus 1 bits of randomness. What are my n plus 1 bits of randomness? That only n bits of randomness. You guys don't know what these n bits of randomness are. That's my, only I know. That's my x. Where am I? Here. My x. What do I give you guys? I give you the first n bits are going to be f of x. These are n bits of randomness. They're all random because f is a permutation. So it takes n random bits to n random bits. So these are n random bits. But I promised you one more bit. My additional bit is going to be the hardcore predicate applied to x. Now, this really has no randomness in it because, you know, from f of x is, I mean, it's hard to invert, but, you know, it's sitting there. I mean, it's a permutation. So f of x determines x, and therefore there's no randomness here. But what I know from hardcore predicate, that from the eyes of a polynomial algorithms or polynomial machines, which is all of you guys, for you, that looks random because it's so hard to predict. You can't predict the probability more than half. In your mind, when I give you p of x, you can't distinguish it from a random bit. So if what I'm giving you has only n bits of randomness, for you, it looks like it has n plus 1 bits of randomness. And the reason is because p of x is a hardcore predicate. So again, you know, it's always like with magicians, they tell you that they have this magic, but then they tell you how you do it, and like, oh, okay, right, okay. So it's kind of a very similar thing here, where you're saying, okay, well, of course, there's no randomness. It's just, I don't know what the predicate. So in my eyes, of course, I can't predict it. That's exactly the point. I'm not really a magician. I mean, you know, a magician doesn't really do magic. It just does magic in the eyes of the bounded, you know, audience. So I'm doing the same thing right here. So p of x does not have any randomness. But for those who are only given f of x and do not know x, it looks random. So that's how I generated for you. one extra bit of randomness. I got only n bits of randomness, and I generated another bit of randomness.
I have
Any
a
questions? Yes.
About the one-way permutation. So for the permutation to be one-way, it has to be the case that for any value in the range is difficult to invert it, right? It's because for factoring, it seems like there are a lot of things in the range that you can easily invert.
Exactly. You're right. So you're right. Okay, yeah. So it needs to be that for a random element in the range, it's very hard to invert. You can't invert except with tiny, like negligible probability. And you're right that my example of factoring was not a good one in that sense. Because there's, you're saying, look, if n is let's say even, I can, but as I said, it's not even a permutation. It has many, an element that is not only a product of two primes. If it has many, if it's a product even of P1, P2, P3, then you can invert it by having P1, P2, and P3, or P1, P2, P3. So my example was actually, not only was it not a one-way permutation, it was not also, as you pointed out, really one way, because any even number, you can easily decompose it to 2 and the number divided by 2. So you're right, my example was only what is called a weak one-way function, which means there's a small set that's hard to invert, but you can convert this weak one-way function to a strong one-way function. So I didn't actually tell you much about how to do that, how to construct, like how to actually construct a really good one-way function. At least not based on factoring. We do have a good, we can construct a one-way permutation based on factoring, but it requires some work. So I didn't show you how to do that. So yeah, what I showed you is just kind of a beginning, but it's not that that's the one-way function. You're completely right.
Thank you.
Yeah, and maybe in one of the TA session we can go over one of these. I didn't put in a homework. Now I'm thinking maybe I should have I could have done a guided kind of question with constructing one-way functions, but I didn't put in the homework assignment. But that's something that you can work out with the TAs in the TA session. Any other question?
I have a question about the hardcore predicate.
Yeah.
You actually, it's a yes or no question. You have efficient algorithm to find the hardcore as the person who has X in fx, but a polynomially bounded algorithm cannot find it.
Good, exactly. So given X, P of X is efficient. So given X, you can efficiently compute P of X. But given F of X, it's very hard to compute P of X. You see,
Yeah,
so if you have X itself, you can easily compute it. But if you only have F of X, it's very hard. And an example you can keep in mind is think of P of X as being one of the bits. Let's say the first bit. So if you have X, computing the first bit of X is very, very easy. But if you have F of X, it may be very hard to compute the first bit of X because it's one way.
Yeah,
Now,
actually,
it may be that the first bit itself is easy, but that's kind of the idea. Yes.
Actually, my question is that, well, you want to ensure that it's a hardcore predicate, and how do you know that? I mean, how do you know that, like, you should take the first bit or the second bit or what?
Great question. So your question is, how do you know what is the hardcore predicate?
Yeah.
Right? You're saying, how do you know which one? So that's that's a very, very good question. I just told you that every F has a predicate, but okay, so yeah, and actually the theorem that says here that every one-way function has a hardcore predicate, they actually show an example of a predicate, but their example is a randomized predicate. So since you asked, I'll say a little bit about it because it's just so beautiful. So here's the predicate. You're right. I don't know if X1 is hardcore, and I don't know if X2 or any single bit, I don't know if it's hardcore. But let me tell you what is hardcore. The randomized predicate, okay, that outputs for a random R outputs the inner product of R and X. So the predicate that's known to be hardcore for any one-way function is a randomized predicate that has randomness R, and the output is essentially kind of sum Ri Xi mod 2, Ri times Xi mod 2. So the inner product mod 2 of the string, bit string R and X. That is the hardcore predicate. So it's a randomized predicate. This theorem is a bit oversimplified. I oversimplified it for the lecture, but essentially what it really says is if you think of f as a randomized function, where f of x and r outputs r and f of x, just add some randomness to it and output this randomness. So instead of f, an input x, output f of x, think of it as being f an input r, an n bit string r, and an n bit string x, outputs r in the clear and f of x. And now the hardcore predicate is going to be the dot product between r and x. That's how you make it a deterministic predicate, if the randomness bothered you. But that's what that's the hardcore predicate that they show is hardcore. And essentially what they show is if for random r you can compute, you can guess r dot x, then you can, it means that I can expect x, you know x. If for random r you can get r dot x, then I can use you to find x. Essentially means you know x. So that's the hardcore predicate.
Great, thank you.
It's a very, I encourage you, if you guys ever have time to look at it, it's really, really a beautiful proof.
Thanks.
Okay, any other questions? Okay, so I'm debating, let me ask you, let me stop sharing screen for a second. I can continue in a bit. I was thinking maybe of giving you guys kind of a 5-minute break to, to move around a little bit. And I find an hour and a half a bit intense. So maybe, feel free to take a break. I'm here. Let's take like just a couple of minutes, like 5-minute break. And I'm here if you have any questions for me or whatever, you can feel free to talk to each other, or I don't know, Jess and Cody, or we can do breakout rooms if you prefer, just kind of 5 minutes to relax a bit.
Breakout rooms could be good. That way we can handle any questions in smaller groups.
Perfect. So can you, can you, Jess, or someone else do the breakout? Oh, Jess, you're muted.
Sorry, I don't seem to have the breakout room ability anymore. So
I think I have. Okay, so let me see. Assign automatically? Yeah, why not?
Yeah.
Oh, wait. Wait, how many breakout rooms should I do? Hold on.
There should be about 50 of us. So I don't know, maybe 10.
Okay. How do I add it? Wait. Do I have an option to options? Oh. How do I know? How can does it give me an option how many breakout rooms to do?
So I have not personally done this, but there should be. Let me see.
Okay.
Yeah, it says you can create up to 50 breakout rooms.
Okay. So where? But where does it give me options? Oh, it's okay. Here I see. Okay, so should I do how many? Do you want 10 rooms? Let's say.
I think that's it. Yeah.
Perfect. Let's see. Have you guys been invited to breakout rooms? Oh yeah, you're going. Okay, so I hope you guys were all talking about how amazing cryptography is, of course. Okay. Okay, great. You see the screen? Okay. Any questions for me before I continue? Okay. So what we saw is how to. I promised that I'll show you how to generate randomness. And here we saw how we generate one bit of randomness. Of course, I hid kind of a lot of the interesting details, which is why, how do we construct a hardcore predicate? Why is it a hardcore predicate? Let's prove that it's a hardcore predicate and so on. But this is just kind of meant as a kind of to give you the high level ideas and as an invitation for you to, try to find out more, maybe take a cryptography class for those of you who haven't, and so on. Okay, but this is, here I just showed you how to generate one bit of randomness. And one bit is not that great. So, what happened? Okay. What we really want is to be able to generate many bits of randomness, not just one. So I want to have a function, we'll call it a pseudo-random generator because it's generating pseudo-random bits. So I want a pseudo-random generator, which is an efficient function that takes a random n-bit string and takes the n bits, but adds, let's say, any big N random looking bits to it. So it generates it maybe leaves the small n, but generates in addition big N number of bits, not just one. And if I have such a thing, then I'm golden. Then I can use it to encrypt n bit for big N bit, for any big N that, like big N bits using the one-time pad. So in other words, suppose I had a function g, that for any big N generated this many bits of randomness. Then this is great. Because what we can do, we can meet ahead of time once. We'll generate only little n bits of key, so little n random bits. And then later, even if we want to encrypt many more bits, oh, that's fine. We'll just stretch our little n bit, random string to many more bits, which we can then use to encrypt. We can use it as a one-time pad. So if we have G that takes only n, small n, and generates big N random bits, then we can use these big N random bits as one-time pad to encode big N bit, to encrypt N bit messages, big N bit messages. Okay, but now the question is, how do we get G that, stretches by big N as opposed to just one? And this I'm leaving for you guys as a homework assignment. I'll let the TAs kind of help you through it, but let me give you a hint, okay? So we showed a G that generator, random bit generator, that takes n bit string and outputs n+1 bit string. But it can take any n bit string, right? So when we have a one-way function, or permutation, it can take any n bit string to n bit string for any n. So now what did we show before? We showed that if I take an n bit string, then I can generate n+1 bits that look random. So now I have an n+1 bit, not random string, but looking like practically random string. So I have an n+1 bit random string, but I want to generate more randomness. What do? I can take that and generate one. I can think of it as a random string. and apply a PRG, as a pseudo-random generator that takes an n+1 bit random string and generates one more n+2 bit random string. And then I can take my n+2 bit random string. It's not random, but it looks random. So for practical purposes, it's random. And apply the PRG, the randomness generator to it to get n+3. So by kind of chaining my pseudorandom generator that outputs, that expands the randomness by 1 bit, I can expand by more and more bits. But why it works and so on, I'll leave that for you as a homework exercise. Okay, and you can do it with the TAs. Okay, so by kind of the point that I want to make is by chaining the generator, the G, the randomness generator, that generated 1 bit, you can get a generator that generates many bits. And this is exactly what we need to do the one-time pad for encryption. But actually, let me tell you more what we can do. And this is really beautiful. I'm not going to have time to show you, but I'm just going to mention it. What we can convert is this generator, the function, the bit generator, the expander, the pseudo-random generator, to what we call a pseudo-random function. So let me tell you what a pseudo-random function is. A pseudo-random function f takes its input consists of 2 parts. The first part you should think of as a key, the key k, and the second part is kind of the input. So the function, the pseudo-random function, takes a key and an input. And the property of the pseudo-random function is that for every big N, think of big N as being polynomial because everything is polynomial. We're only talking about kind of polynomially bounded adversaries. So kind of our world is polynomial. So for any big N, that's polynomial. And for any x1 up to xn, as long as they're distinct, it can be 1, 2, 3 up to n, whatever you want. For any x1 up to xn, if you look at f with a key on x1 and f with the same key on x2, and so on and so forth, it all looks like a uniform and big N bit string. So this function, if you take a random key, everywhere it looks random. On every single input, it looks random. And on any group of inputs, on any set of inputs, it looks random, unless, of course, you have the same x twice, and then you get the same value because this function is deterministic. But as long as these x's are distinct, it just looks like these n. Think of the function as going to 0, 1 for simplicity, as opposed to larger. Just think of it as outputting a bit. Then this function, a pseudo-random function, on any set of distinct input just outputs together, they're all looking random. Now, of course, they're not really random. I can't really generate randomness, but they look random. That is what's called a pseudo-random function. Okay, it's a function that looks like, when you ask the function, if you don't know the key, and you ask for the function, oh, I want to know the function on x1, and then you say, okay, actually, I want to know the function on x2, and then you say, actually, I want to know the function on x3. Whatever you ask, it just looks like a random function. You cannot distinguish between this function by the values. You can't distinguish between the function and just a completely random function. Okay, this is what's called a pseudo-random function. The reason why this is not really random is because it's a deterministic function. It's a succinct, it's a polynomial time computable deterministic function that has only a little bit of randomness associated with it, which is the key. The rest of it is completely deterministic. And what's known is that given a pseudo-random generator that actually takes n bits to 2n bits, that stretches it by 2, you can construct a pseudo-random function. So I won't show you how to construct a pseudo-random function, but it's a very nice tree-based construction. Again, it's very beautiful, but I don't want to overwhelm you. So I don't want to give too many details. But if you have you know, what we started by saying, if you have a pseudorandom generator that expands by 1 bit, generates only 1 bit of randomness, you can use the pseudorandom generator to generate more randomness. Okay, you can generate any, so you can go, let's say, from n bits to 2n bits of randomness or more. And now I'm arguing, even though I'm not showing you anything about why, that you can take a PRG that takes an n-bit random string and generates something that looks random of length 2n bits, and you can take that to create what we call here a pseudorandom function. And now once we have a pseudorandom function, then we have kind of a very nice encryption scheme. And here is the encryption scheme, where it's many time, it's stateless, it's very nice, and here it is. How do I encrypt? Oh, sorry, I forgot here a K. There's a key. So here's an encryption scheme. It takes as input a key K, which I forgot to write right here, and a message M. And here's what it does. It chooses our random input, R, to the function F. I'll tell you why I use randomness in a second. But it takes a random input R, and then it masks M, the message M, using the one-time pad. But the pad is F of K and R. Okay, it's the function. So think of M, I'm encrypting here bit by bit. Think of the message I want to encrypt as bit. If you want to encrypt the long message, just break it down to bits and encrypt each bit separately. This is my encryption. And now I want to argue I can use this to encrypt many, many times. Okay, so let's pause here for a second. I want to ask a few questions. Question number 1, why do we use randomness? Why am I choosing R at random? Why not take, I don't know, a fixed, the 0, the 1, I don't know, something else.
Should we answer in chat or?
No, give ideas. No, not at all. Talk.
I think it's because if our choices are predictable, then our encryption scheme is not safe. Like if somebody can predict what we're using to encrypt the input, then they can have the input.
Okay, so let me break down your answer, because some of it is correct and some of it is incorrect. But okay, here, you know, okay, here I'm giving R. It's not like I'm not giving R. Actually, R is part of the encryption, and it's very important that R is part of the encryption, because if I'm not giving R, you can't decrypt. The way that the receiver is going to decrypt is because he knows the key and he knows R, so he can compute the pad. The pad is like the secret for the one-time pad. So he can compute FKR and then demask M. Okay, and then he can kind of get rid of this mask by XORing with FK and R to get back M. So R here is public. And actually, let me say another thing. R does not have to be completely random. It just needs to be, I think that's what you meant by unpredictable. It needs to have high min entropy in a sense. So the only important thing is that we do not use the same R twice. The reason I said we choose it random, and I think that's kind of what you meant maybe, is by unpredictable, is we need to ensure that we don't use the same R twice. If we use the same R twice, it's essentially like we're using the one-time pad twice, which we said is not good. The one-time pad we can really use once. But if we use each R only once, then we're using each pad. Because if the R's are distinct, the R's correspond here to the X's. If the R's are distinct, all these pads are just look random. So all we need in this encryption is that we don't reuse the same, that the R's are distinct. And how do we ensure that the R's are distinct? Either we have a stateful scheme that we say, okay, first we use, you know, number 1, then we use number 2. Like first we encrypt using FKN1, and then we encrypt using FKN2, and then we need to remember the state. You know, we need to remember, oh, we encrypted so far n bits, and now we use n+1. So if you have a stateful kind of a encryption, you don't need randomness. But if you have stateless encryption, where the encryption function only takes K and F, that's it. There's no state of how many elements were encrypted and so on, then it has to be determined. It has to be. Then this encryption scheme, it needs to be random, okay? Because otherwise, if it's determined, if the R is determined, you're going to use the same R twice. So it has to be random. It doesn't have to be truly random. It's enough for it to have as long as there's no collision. So as long as R is sampled from a distribution that we won't see the same R twice, then it's good enough. And let me tell you something interesting. We know that for stateless encryption scheme, where the encryption is really just a function of the key in the message, it has to be randomized. If it's not randomized, it's not really secure. When secure, I mean according to our many times security definition. So what is our many times security definition? It says that for any L number of messages, and for every like two sets of like messages M1 up to ML and M1 prime up to ML prime, if I give you encryption of the messages M1 up to ML with a random key K, or I give you encryption of the messages M1 prime up to ML prime with the same key K, you can't tell the difference. It looks the same. That's the security we want. And to achieve the security, we have to have some randomness. We have to use randomness. Kind of interesting that to get like many times security, you need randomness. Anybody see kind of an example why you need randomness? Like a clear attack for any scheme that does not use randomness? Okay, it's a bit subtle, so let me give you the example. Suppose I encrypt the same message twice, okay? Let's say I want to say yes. There's a question, we're at war, and I get a question from the US Army saying, should we attack? And I want to say yes. If it's deterministic, every time I say yes, I'll get the same ciphertext. There's the deterministic function of the key, same key, and the same message. So I'm going to get the same ciphertext. Now that is very insecure. Generating the same ciphertext for the same message is not something we want. And the example is exactly, suppose my messages are very short, just yes, no. And once you learn what you can, for example, why is it so dangerous? Because, for example, suppose once I'm the American Army, the Soviet Union are sitting there on the line, and they know that my answer now is yes. Maybe they know that every morning, I get a question, do you want coffee? And every morning I say yes. And so they know now what a yes is. And then later there's a message of saying, oh, should we attack? And I say yes. Now they know the yes. So it's very important that even though the same message is encrypted twice, it looks completely random. This is for every element of ML, not necessarily distinct. If all are the same here and all the ends are different here, the distribution should look the same. And that's why you have to have randomness unless you're stateful somehow. Like you somehow keep state of how many messages you encrypted so far and so on and so forth. But if you just use this kind of mechanism, this syntax, then you have to have randomness. Okay, so we're out of time, but that's good. That's all I wanted to tell you. So here's the homework. You'll have it on I just put in the slide. We have one homework on one-time program, one on pseudorandom generators, and the other one is so beautiful. It's not simple, but it's something that maybe the TAs will help you work through, and it's very, very nice. It's kind of a pathway to what's called public key cryptography, how to encrypt messages while never meeting before to agree on a key. So it's really mind-blowing as well. It's kind of another kind of magic that happens in crypto. But let me just do a quick recap before we, actually, let me stop sharing the screen and just tell you a quick recap before we break. So what did we talk today? We showed that, there's this one-time pad, it's very beautiful, but you can use it only once. And then we showed if you want to do many times, it's impossible unless you somehow generate randomness out of thin air. Generate randomness out of thin air is of course impossible, but what we can do is generate random looking bits from hardness. And that's the hardcore predicate. And so now once we assume that all our adversaries are computationally bounded, are polynomial time algorithms, then we can fool them to think that we generate randomness by just giving them something that's really, really, really hard to predict. And that's what we do. We generate in our encryption schemes. We show how to generate randomness using hardcore predicate. We kind of do a chain rule kind of thing. That's what you'll do in the homework to generate many bits of randomness, let's say from n bits to 2n bits. Given that, there's a way to generate pseudorandom functions, which I didn't tell you about, some very beautiful tree construction that I omitted from this lecture. But then once you have the pseudorandom function, what we saw in the last part, the last slide, is how to use that to generate any many times secure encryption that is secure against polynomial bounded algorithms or adversaries. Okay, so that kind of was a quick summary. And next lecture on Thursday, I'm going to show you a really, really beautiful kind of idea of zero knowledge proofs. Okay, so thank you, and I'll see you then. Bye. I'm here, by the way, for questions. If anybody has questions and you want to ask, I'm here.
I have a question.
Yeah.
Would you like me to leave the recording on for the question, or would you like me to turn it off? Just wanted to.
Again, sorry.
Would you like me to stop the recording for questions or keep it running?
I don't care, whatever. Let's keep it in case someone wants it. I don't know. Or up to you guys. Yeah, I don't care. Yeah. Okay, questions.
Yeah, so for the first function you introduced where we take in a random key and output a bunch of random bits, you had mentioned that like one of the reasons this wasn't possible since we can't generate entropy out of thin air. So I'm just wondering with the pseudo-random generators if that's an issue in terms of kind of replicating or looking random, that we might have less entropy.
Okay, so sorry, Cassandra, can you repeat your question? I'm not sure I understood it.
Oh yeah, I'm just wondering, so if we can't generate entropy out of thin air, I'm guessing that like the random bits we generate will have kind of less entropy overall.
Right. Yeah, so actually we're not generating any randomness. What we're generating is something that looks random. So remember, like our additional bit that we're like in our construction, the additional bit is a hardcore predicate. It's some P applied to X. This is not random by any means. It's actually deterministic. But it looks like it's random. So to the eye of the audience, of the world, of the adversaries, it looked like we're generating randomness out of thin air. But to us, that we know the X we started with, it's not, there's no randomness there. Like we started with a random string X and what we append is just P of X, very deterministic, actually efficiently computable if you know X. But if all you know is F of X, then you think we generated randomness. We didn't. What do you think it is? It looks random. It's exactly like you think, you know, the magician cut the woman in half. He didn't cut her, but it looked like he did. So does that answer your question?
Yeah, I think so. Thanks.
Okay, sure. Any other questions?
I'll ask one. Maybe it's two questions, but it's about the hardcore bit construction. You said that the proof gives a randomized function that is guaranteed to be hardcore for every one-way function. Is it the case that there is a deterministic function for if I give you a specific one-way function, can you turn it into deterministic hardcore?
Good, good. That's a very good question. So that's a great question. So I want to repeat because it's such a good question. So you're asking the following. First, you're asking, is it true that for any one-way function X, there's a deterministic one-way predicate, like hardcore predicate P? The answer is we don't know. It's a very open problem. We don't know the answer. What we do know, there do exist some one-way function, like the discrete log-based, like input X, output G to the X. And for that, we do know that, we do know that there's some specific bits that are hardcore. So we do know of some one-way function that have deterministic hardcore predicates, and even these predicates are bits. It's like the most significant bit or the least significant bit. I don't remember exactly, but we know specific bits that are hardcore. But it's not. We don't know a generic answer to that, like that whether every one-way function has a deterministic hardcore predicate.
Thanks.
Sure. Any other questions? I see that there's things in the chat, but oh, thank you. Okay. Yeah, thank you. Okay, guys, so thank you so much for your attention. If I'm on Slack if you have any other questions, and the TAs can, of course, answer any questions you have in the TA slots. So thanks again. I'll see you guys on Thursday. Yeah. Okay, bye, guys.